Today we're looking at electric fields and energy. A lot of times in science fiction and fantasy, heroes are given superpowers to manipulate the force, to shoot and cast spells, to dispel darkness and evil. In nature, we have the same thing. In nature, there are many types of force fields to push on something without actually touching it. Force fields exist in regions of space surrounding certain objects that have properties. And in this case, there are two main force fields we encounter in day-to-day life. The first kind that we're more familiar with are gravitational fields. Gravitational fields act on masses. Their strength is proportional to the amount of mass present and inversely proportional to the distance squared, inverse square law. So for example, if you're twice as close to the Earth, the gravitational field is not twice as strong, but 4 times stronger. And conversely, if you're 5 times further away, it would be not 5 times weaker, but 25 times weaker. And then gravitational fields are always attractive. They hold the Earth in orbit around the sun, the moon in orbit around the Earth, etc. You can't shield a gravitational field, at least we don't know how to do that yet. And lastly, you can store up energy in a gravitational field. And when we go to Six Flags Great America, big time, you experience gravitational potential energy as you lift a coaster to the top of its first hill, and then you release all that potential energy stored against gravity to kinetic energy through loops, turns, boomerang, hills, etc. Electrical fields are similar to gravitational fields. However, they act on charges, not masses. Their strength is proportional to the amount of charge present and also inversely proportional to the distance squared. Unlike gravitational fields, electrical fields can attract or repel charges. Electrical fields can be shielded, which is really cool. And also, electric fields can store up energy. In other words, all of modern life is made convenient and possible because we can manipulate electrical fields to store up energy, your battery, to run your cell phone, laptop, etc. And then we can move those charges around to do cool things like send your texts, get your emails, snap pictures, etc. Next, let's define the electric field. Electric field has a very simple definition. It is a force field that acts on other charges. It surrounds a space around a source of charge, whether it be positive or negative, and it's defined by a force on a positive test charge. Think of it like you're testing it with a positive hockey puck that gets slapped around the ice, but in this case, the ice is a field of charges. The equation we're going to use is E, which stands for the electric field, is equal to F, the force, divided by Q, the charge there. And technically, the electric field has units of newtons per coulomb because force is measured in newtons in honor of Sir Isaac Newton, and Q, charge, is measured in coulombs in honor of Charles Coulomb, coming up with Coulomb's law for electrical force on static charges. Last thing to point out is electric field is a vector. It has both magnitude and direction. So sometimes in a textbook you'll see a little arrow on top to represent that, or it might be in bold for E and F there. For us, we'll just keep it simple. We'll just say E equals F divided by Q. Next, let's look at the electric field in terms of Coulomb's law. If we take Coulomb's law, which is F equals K, Q1, Q2 over the distance squared, we can factor out Q1, which is going to be our positive test charge. So if we do that, we can simplify force equation by rewriting it as simply F equals Q1 times E, the electric field, where electric field E is the second part, KQ2 over the distance squared, where now Q1 is the force on our test charge, and now the E statement is a field created by the charge Q2. So in other words, we can find the strength of an electric field if we know the amount of charge we put there. So in other words, more charge, stronger force field, kind of makes sense. And then it's inversely proportional to the distance squared, and we multiply by the Coulomb's constant, 9 times 10 to the 9th Newton meters squared over Coulomb squared, to give us the size of our electric field. So in other words, Coulomb's law is how we can actually derive the actual strength of that electric field if we know the amount of charge present and the distance we are from that source of charge. So now we have a little electric fields concept check question to see if you know what's going on. So the question reads, the electric field in a certain region of space is 40 newtons per coulomb. A, what is the force on a negative 10 coulomb charge placed in that region? And then B, is this going to be an attractive or repulsive force? I want to point out this isn't a normal calculation the everyday person would do, but if you're an electrical engineer working for Apple and you're working on the next iPhone battery, this might be a type of calculation you'd actually need to figure out. Let's give you a minute, see if you can break this down using the equations we just came up with.